Most tree traversal involves recursion, and the most common algorithms are breadth-first search and depth-first search. Depth-first search has in-order, pre-order, and post-order. In-order is normally used in binary search trees because we need to identify the left and right nodes. I'll be making another video on in-order non-binary trees. Stay tuned for that. When I was reviewing a problem that involves tree traversal, I was particularly stuck on the call stack for depth-first search post-order. Post-order is best used for tree deletion because we need to make sure to delete all branches before we delete the root to prevent memory leak. So I'll be spending a little time today explaining post-order call stack. To quickly go over each algorithm, breadth-first search goes level by level. If the parent node has children, it will finish visiting these children before moving on to the next level. Depth-first search goes branch by branch. In-order visits all the left children nodes first, the parent node, then the right children nodes. Pre-order visits the root, all the children nodes, and sibling nodes. And post-order visits all the children nodes before the parent node. So we have the prompt here. It goes, write a series of iterator functions that demonstrates the tree traversals. Each function takes a node of the tree and a callback function. The function will iterate through the child nodes, calling the callback function on each of them. The difference between them is the order in which they iterate. So we have a setup here. It gives us the structure of the tree we'll be traversing. We initiated a node function that returns an object. So the node has two properties, value and children. The tree looks like this. And we'll be using node logger as our callback function. So let's go over the table and the order for each traversal. For breadth-first search or level order, it goes level by level. So the order the nodes will be visited is A, B, C, D, E, F, G, H, I, J, K, L, M. This is exactly what we expect. Everything is in order. For depth-first search pre-order, all the children nodes are visited before sibling nodes. So we visited the root first, the left children, then the right children. So it goes A, B, E, K, L, C, F, G, H, M, D, I, J. This is the order that is supposed to be. Then for depth-first search post-order, we visit all the children first before the parent node. We visit the left children first, then the right children, then the parent node. So the order goes K, L, E, B, F, G, M, H, C, I, J, D, A. This is the order for post-order. Now let's look at the functions. The solution for breadth-first search and depth-first search pre-order are pretty straightforward. For breadth-first search, we implement a queue that stores the nodes. As long as the queue is not empty, we pop off the first node of the queue, call the callback function on the node. Then we push the node's children onto the queue. Then the process repeats. So line 44 is important because every time we run the loop, the variable is reassigned to a different node to prevent an infinite loop. In depth-first search pre-order, it calls the callback function on the parent node first, then recursively calls its children. One might ask, where is the base case in this function? I was wondering that myself, so I did some investigation. The setup initialized an empty array for children, right here. In common practice, the stopping case for recursively traversing a tree node is to check if the child node exists, or is null or falsy. In this case, we don't have to include a conditional statement for a base case because the for each method runs on undefined and null, but won't run on an empty array, which stops the recursion when there is no children. Now onto the post-order solution. I drew a diagram for the call stack. When we first run the function, it's going to recursively traverse through all the children until there's no children, and visit the leaves by calling the callback function on them. This is the correct order, and let's see how the call stack works. So when we first run the function, A goes on the stack. A has three children, B, C, D. The first child being called is B, so B goes on the stack. B also has a child, E. E goes on the stack. E has two children, K and L. But K and L have no child, and K is the first one being called. So K goes on the stack. Now, because K has no child, it's ready to be visited and being called by the callback function. So now it gets popped off the stack and logged. L is the same case. L has no child, so is ready to be visited. So it gets called by the callback function, gets popped off the stack, and logged. So E is done now. E is finished with traversing and is ready to be visited. So E gets popped off the stack and logged. Now B is done traversing and ready to be visited. So it gets popped off the stack and logged. We're back to A, but A is not done. A still has children C and D. So the next child being called is C. C goes on the stack, and C has 3 children, F, G, H. But F, G has no child. So the first child being called is F. F goes on the stack. Since it has no child, it's ready to be visited. And it gets popped off the stack, logged. Same thing with G. G is ready to be visited, gets popped off the stack, and logged. So now we have H, but H has a child, M, so it's not ready to be visited. We have to visit M first. M has no child, so M is ready to be called by the callback function, gets popped off the stack, and logged. So now H is done traversing and is ready to be visited, gets popped off the stack, and logged. C is now ready to be visited, gets popped off, and logged. We're back at A now, but A is still not done. A still has the last child, D. So D goes on the stack, but D has 2 children, I and J. I has no child, so I is ready to be visited. It goes on the stack, gets called by the callback function, gets popped off and logged. Same thing with J. J has no child, is ready to be visited, gets popped off and logged. So now D is done traversing, is ready to be visited, gets popped off and logged. So we finally back at A, and A is done with all the children and is now ready to be visited. So it gets called by the callback function, gets popped off the stack and logged. This is how the call stack works for post-order tree traversal. If we run function, you can see it's exactly the order we want right here. Analyzing and explaining tree traversal stack honestly has helped me understanding algorithm a lot more. I hope my explanation was clear and helpful. Again, thank you for watching.